very challenging research issues. And I'm not giving any further information because I think that you already have the necessary information that would allow you to learn more also by studying independently. Perfect. Now, the next step that we have to make is to see at least an example of a more complicated model. Because for now, we considered a couple of models. One, we considered together, the linear reservoir. The other one, I gave you some information to study independently, the lead time barrier. And these are basic hydrological models. In a course of advanced hydrology, we have to consider at least one advanced model. So let me move a step forward. And basically, this step forward is moved by referring to the slides that in my website are called, again, Rain-Foranov modeling. So I went a bit forward to the slides called calibration and validation. Now I'm stepping back to Rain-Foranov modeling. And please note that the slides dedicated to Rain-Foranov modeling, I updated them yesterday because I made some changes, because I changed the notation basically. So if you downloaded them, please download them again. Now I'm working on the blackboard, and I just want to open the PC because I want to use the same symbols. But so I'm working on the blackboard. You don't need to download them now. But when you will prepare the subject, or maybe if you want to check what's going on the slides, download them again. Just 1 second, because I want to make an effort to use the same symbols. And so I said I'm moving a step forward, and the model that I'm now going to consider is still a lumped model. You may remember what a lumped model is in contrast with a spatially distributed model. A lumped model is applied to the whole catchment, doesn't split the catchment in sub-pieces. So it's still a lumped model, but with respect to the linear models that we used so far, this model is more appropriate for continuous simulation. You may remember the difference between event simulation and continuous simulation. I said that event models are meant to reproduce only one event, typically is a flood. Continuous simulation models are meant to reproduce long time periods of data. And of course, continuous simulation in water resources management is more relevant because, as we said, we want to produce long series of data related to water resources availability. So, even if, in principle, the time area method and the linear reservoir could be used for continuous simulation, actually they are often used for event simulation. While the model that I am introducing now, it's a model that lends itself better to continuous simulation. And in fact, it's a model that is largely used in water resources management. Now, how is the model called? The model is called IMOD, and IMOD stands for hydrological model, so the author of the model didn't have really a lot of creativity when he decided how to call it. I'm just opening the PowerPoint, and so it's called IMOD. And let me make a premise before introducing the model. What is the main limitation of the linear reservoir? The main limitation is that the linear reservoir assumes that the catchment is like a tank with a water storage in it. And, you know, this is not very realistic because I said that the catchment is heterogeneous. It's not homogeneous. A tank is an homogeneous matter. And let me try to better explain. If you think of the storage in the tank, this is a storage that is average over the catchment, and actually, this storage is assumed to be not upper bounded. It's not upper bounded. If you put a lot of rain into the linear reservoir, you get a storage WT that increases and may tend to infinity. This is not really meaningful from a physical point of view, you understand that. What happens in a catchment? In a catchment, it happens that if it rains a lot, the catchment gets saturated. And this is a situation where we get concerned a lot, because if it rains over a saturated catchment, it means that all the rainfall, or almost all the rainfall, is converted into river flow. So this is a behavior that we want to reproduce, because it's extremely important. And the storage is also important for water resources management, because if you get a model that may get a storage that tends to infinity, it means that before depleting, before exhausting this storage, it may take a long time. In the reality, the storage is upper bounded, and this means that the catchment could get dry, in the reality, quicker with respect to our model. So this is you know, a behavior that we want to reproduce. So first of all, the fact that the storage is not upper bounded. The storage in a catchment is upper bounded. And second, there is another important consideration. If you define a maximum storage for a catchment, this is spatially varied. You may have portion of catchment that are impervious, which means zero storage, zero potential storage. You may have other areas which are very permeable, that have a very significant potential storage. And this is an important behavior, because today, for instance, we are concerned by urbanization. Urbanization makes the surface of the catchment impervious and reduces the potential storage of the catchment. And it reduces it only locally. So all of these behaviors are not accounted for by the linear reservoir model. The linear reservoir just assumes that the catchment can store water, and there is no upper bound to this storage. Actually, we have a potential maximum storage, a maximum potential storage, and this maximum potential storage is spatially variable. So basically, you can understand why people decided to apply distributed model, because they wanted to take into account these behaviors. And you may understand why people devised more complicated models. They wanted to take into account these behaviors. But on the other hand, of course, this is complicated, because you need, at least it is complicated because you need a lot of information. So let's suppose that you want to reproduce these behaviors that I introduced. You want to reproduce that the catchment has a maximum potential storage that changes over space. Then you need local measurements of soil type, land cover, land use changes, land use and land use changes. You need local information of all these features of the catchment if you want to estimate at the local scale, like here, where I'm staying, the maximum potential storage. So on the one hand, you want to be more detailed, you want to reproduce these behaviors which are fundamental in rainfall runoff modeling. On the other hand, you need a lot of information, and this is one big challenge. And then there are also other challenges, like the fact that you need computational means, but the information is a big issue. So how can we resolve that? So basically people started to think at possible solutions for trying to reproduce these features while keeping the amount of information manageable. And of course, this means that you have to make approximation. You have to describe processes in a simplified way. And therefore, people started to brainstorm, to develop ideas for making the models more realistic while keeping a simple representation. And I think that this IMAP model is an excellent example. When we look at the code, the computer code for applying this model, it could stay in a blackboard. It's very limited. But still, you will see that the model is a very significant step forward. So actually, the idea was to take into account, when proposing this model belongs to a wider class of models, so we will look only at this one. The idea was, when proposing this model, to take into account that the catchment has a maximum potential storage of water, and this maximum potential storage is spatially varying. And therefore, while keeping into account that the information was limited and is limited, so while keeping into account that it's impossible to define at local scale what is the maximum potential storage, the idea was to keep into account at least that it's spatially varying. So one first idea was, okay, let's define the maximum potential storage with a parameter, and let's assume that this maximum potential storage is spatially variable. Okay, so basically let me make a sketch. And let's suppose we started from this situation in a reservoir where we had a tank with a unique value for storage. It was W. T. Now, let's suppose that the catchment is again given in a conceptual scheme by a tank, but this tank is divided in many different sub-tanks. And let's assume that these sub-tanks have maximum potential storage, which can vary from 0 for impervious areas to a maximum that we call Cmax. So let's suppose that. Oops, sorry. Let's suppose that this is the maximum potential storage of these tanks. So basically, if it is like that, I can delete these walls and represent the catchment as a tank like that. This is not really nice because it's not nice to represent the catchment like a tilted slope. So in my slides you will see a different representation which is equivalent, and the different representation is the catchment is flat, but it's the catchment is flat, it's the bottom that is tilted. Doesn't matter. I can write an or here. And then here you can put trees and etc. Houses, because here you don't have much storage, so you can assume that there are houses here and etc. Doesn't matter. The idea is to represent the catchment surface, and below that the storage, the maximum potential storage. Now what happens if it rains there? And let's suppose that you get a rain. You get a rain, let's call it PT. And let's consider, for dealing with this model, that this is not a volume of rain, it's a depth of rain. Okay? Let's call PT as the rainfall depth, and let me also say that in our treatment of this model, PT is the cumulative rainfall depth. Cumulative means that you start from a time t equal to 0 and you sum the rainfall up to time t. So it's an ever increasing, or let me say, not decreasing variable. PT is cumulative rainfall. Cumulative rainfall depth. So what happens if it rains over there with a nice PT? And let me, I don't have another chalk, but anyway, let me assume that this PT, I would like to make, let me move this house, okay? Because here it's, for me, it's a bit, so let me put it here. Okay, now let's suppose that this rain PT can be indicated with this depth. So this is PT. Which rains uniformly over the catchment. So this is a lamp model, so we still assume that PT is a uniform rain over the catchment. And then the same rainfall can be indicated here, PT, and then we can get this picture, which is the same picture that you find on my slides. So what happens in this case? So basically keep in mind that what you see here in brown is the maximum potential storage over the catchment. And therefore you see that when it rains, some rain falls over impervious areas, some rain falls over areas that have a high potential storage. And therefore your immediate intuition is that what you see here is rain that doesn't infiltrate. It flows over the ground. Instead, the contribution that I'm now highlighting here, this contributes to infiltration. It's stored in the catchment. So basically, what do you see here? You see a situation in which, as soon as it starts raining, you get some, what is called overland flow, and some infiltration. Fine. And what happens if you get additional rain? And this could be T plus 1. If you get additional rain, then you have a part that infiltrates, that flows, this one, and the part that still infiltrates.
In this case, we don't take into account that the fact that the time is passing. So, in the T plus 1, why there is less infiltration than in the first case? Because
there is less infiltration because the catchment is more saturated than before.
Okay, but for example, if T plus 1 is 1 hour later,
yeah,
after T,
yeah,
maybe the catchment
dries.
Yeah.
Okay, perfect. Good question. Okay, we are assuming in this scheme, and we will keep this assumption for a while. We assume that there is no depletion of the catchment storage. And I anticipate that this model takes into account, this model allows for depletion of catchment storage, but it allows that not through a bottom discharge, as it was done for the linear reservoir. It allows that for the effect of evaporation. But let me start introducing this model by assuming that we don't have any depletion of catchment storage, we don't have any evaporation. This is an important assumption that I will remove. But for now, for making this model simpler to understand, this is, I think, a very useful assumption. So let's assume that we move towards saturation as rainfall increases, and we don't have any drying effect in the catchment. Is this clear? Perfect. And you know, it's a simplifying assumption because you already understand, and he already understood, that if you introduce a depletion term, the model becomes more complicated. So let's suppose for now that...
Excuse me.
Yeah.
Could you please repeat what happens when we add PT plus 1 on
Yes.
that surface?
Yes. Remember that P is cumulative rainfall, so either it doesn't rain and therefore it remains unchanged, or it increases. So let me suppose that it increases, and then if it increases, it means that in each of these sub-reservoirs you increase your level of storage, because we don't have any depletion term. So basically, when you add this band here, you have a part that rains over sub-storages that are already saturated, and this part is, everything is overland flow. The other part rains over storages that can still receive water, so this is the contribution to infiltration. Of course, if it rains again, you get to a situation where the whole catchment is saturated.
I got it.
Okay.
Thank you.
And okay, so far this is a brilliant idea, but it remains the problem that you need to estimate these storages, these individual storages. Now, let's suppose that we are not interested in knowing where these storages are. Let's suppose that we are just interested in getting an estimate of the overland flow of our river discharge, basically, and an estimate of the water that is stored into the catchment. So basically, we are not interested in knowing where these storages are, but we need to know, we just need to know their amount. And their amount can be quantified through parameters. So this is, again, another idea. And by intuition, if you assume that you have some impervious area into the catchment, and if you want to estimate these storages, what are the parameters that you need to introduce? First of all, you need to estimate, you need to define the maximum. So you need a parameter to define the maximum potential storage over the catchment. You need to define the maximum one of these. Otherwise, if I don't define the maximum, I cannot draw this picture, this triangle. So I need to define the maximum. The maximum is Cmax. This is the parameter. Perfect. So basically now, what I have to define, because you see, I need to draw this picture. So I assume that I start from 0. I go to Cmax. And then I need to define what is the progress of this distribution over the catchment. I don't need to define where these storages are, but I need to define how these storages change, vary from 0 to Cmax. Because if I were able to draw this triangle, and again, I'm not interested in knowing where this storage is, but I need to define this triangle if I want to compute the discharge and the infiltration. So basically, I need for sure the parameter Cmax, And then you may say, that's it, because if I assume that, if I assume that the change is linear, the progress is linear, that's fine. From 0 to C max, it's a linear progress. But linear, you know, it's a bit restrictive. Because what I'm trying to describe is the distribution over the catchment of these storages, potential storages. A linear progress, it's a bit restrictive. So, who proposed this model said, okay, let me try to allow for a more flexible interpretation. He wanted to, you know, to be able to introduce a curve like this one, for instance, or like this one. And therefore, we need additional parameters for describing the progress from 0 to C max. And this model assumes that this progress is given by a relationship, an analytical relationship, which now I am introducing. And let me call it, this analytical relationship, the dependent variable. Let me define it and call it as FC. So C is the storage, which varies from 0 to C max. And what is F? F is, and I will repeat this definition, the percentage, or let me say the percentage expressed between 0 and 1. So percentage is not really the fraction. Let me say the fraction, F is the fraction of the catchment that has a storage which is less or equal to C. Again, what is F? F is the fraction of the catchment. So F may stand for fraction that has a storage that is less or equal to C. So, if it is defined in this way, what is F of C max? What is F of C max? What is the fraction of the catchment that has a storage that is less or equal than C max? It's 1. What is F of 0? It's 0. Okay, now let me define FC in this way. 1 minus C over C max to the power of beta. And you may say, oh, what a complicated relationship. Not really. I will show you that it's not very complicated. Okay, so in order to better understand how it behaves, let's make a graph. We are engineers, so we don't like really to see analytical relationship. We want to see things. So let me draw a graph. And let me put FC, FC here. And let me put, so FC varies from 0 to 1. And let me put C here, from 0 to C max. Can you see here? Everybody of you can see? Okay. And basically, I already know that F of C max is 1. And F0 is 0. Okay. So, let's suppose that beta is equal to 1. And let's see what the shape of this relationship for beta equal to 1. If beta is equal to 1, it disappears. it's an exponent which assumes unit value, and FC is 1 minus 1, they cancel each other, and plus C divided C max. So FC is equal to C divided C max. What happens then? Linear variation. This is beta equal 1. So you see that as a special case, I go back to this triangle here. Yeah, it's not really straight, this line, sorry. Okay, now, what happens if beta tends to 0? And basically, if beta is 0, basically you have here that this quantity between parentheses takes an identical value of 1. So FC is identically 0. What does it mean? So basically, if beta is equal to 0, it means that for any value of C, the fraction of catchment that has a potential storage lower or equal to C is 0, which means that basically you always have no part in the catchment that has lower or equal infiltration, which means that the storage is identically equal to C max over the catchment. So the storage is not spatially varying, it's taking the value of C max everywhere. So basically, in order to depict it here, I would say that it's something like for beta tending to 0, the curve is like that. So this is beta tending to 0. No, sorry, it's the opposite, because F is identically 0, so basically it's here, it's like that. This is beta tending to 0. It's not really beta equal to 0, because beta equal to 0 would be identically 0. But for beta, I prefer to use, to visualize what happens for beta tending to 0. The curve is getting closer and closer to the abscissa. The other curve that I depicted here is for beta tending to infinity. What happens if beta tends to infinity? Basically, keep in mind that this quantity is lower or equal to 1. Let's suppose that it's lower than 1, because let's see what happens for C tending to C max, but lower than C max. Basically, you have a quantity that is lower than 1, elevated to infinity, means that you get to 0, close to 0. So the curve gets close to FC identically equal to 1, which means that the catchment is getting impervious with no potential storage. So let me write here that beta tending to 0 means C equal to C max, and beta tending to infinity means C equal 0.
So that defines the reason why it's cumulative, right?
Yeah.
Because CDF is below.
Yes.
0 and 1.
Yes. And what it's important to notice is that, you know, this relationship, which there is no other solution for you than learning it by memory, this relationship has a motivation, because for varying values of beta, you describe several possible curves with a lot of flexibility, which are included between these two extreme situations, where you don't have any storage in the catchment, and you have a spatially distributed, spatially uniform storage equal to Cmax. So basically, you define the distribution of the storage in a very flexible way with two parameters, Cmax and beta. I think we can stop here, and what I suggest to you, first of all, let me make the plan for next week. Next week, Tuesday, is degree day, but the lectures are suspended only up to 3 o'clock. We have lecture at 4, so I will lecture on Tuesday. I hope you don't have anything against, because you may have heard that on Tuesday the lectures are suspended. And I think also on Wednesday, but I'm not sure. For Wednesday, I'm not sure, because I am not teaching, so I didn't pay attention. But for Tuesday, lectures are suspended up to 3 o'clock. And I couldn't make any lecture. I'm not allowed to make a lecture before 3 o'clock. But given that we have lectures, we are lecturing at 4 o'clock, I will lecture, okay? So we will see each other on Tuesday, same room. And then I will lecture on Thursday, and then PC on Friday with Emanuele. Okay? This is the plan for next week. Before Tuesday I will be able to complete the treatment of this model. I suggest before Tuesday pay just half an hour of time to better get how this relationship and this analytical relationship behaves. Okay? It would be better and helpful for you to better get the